Hi, I'm Dr. Ben Britton, and I'm going to be talking to you now about the use of energy dispersive X-ray spectroscopy, which is otherwise known as EDX or EDS. I'm a reader in microscopy and my metallurgy in the Department of Materials at Imperial College London. So why do we want to use EDX? So it's a chemical spectroscopy. It's equipped in many SEMs that we have access to in our labs. The electron probe can be used to stimulate the production of characteristic X-rays. These characteristic X-rays can then be analysed to give you local chemical composition, and the technique is usable both in the transmission electron microscope, the TEM, and the scanning electron microscope, the SEM. The technique itself is complementary to a variety of other techniques, including energy electron loss spectroscopy, or EELS, wavelength dispersive X-ray spectroscopy, or WDX, and electron backscatter diffraction, EBSD. There's a range of others it's useful for as well, you can just imagine. The fundamentals of the technique is that we have a high energy incoming electron. That incoming electron will promote a core electron to a high energy state. That core electron will fall back down to its preferred energy state, and in the process it will release a characteristic X-ray corresponding to that electron transition. We have a EDX detector that measures the energy of those generated X-rays, and if we can characterize those characteristic peaks, we can work out what species was present. Of course, there are a number of other X-rays that will be generated. One major thing we have to consider is the Bremsstrahlung, or the braking X-rays. These are generated as the electrons slow down within the material as they are scattered. Photons will be generated corresponding to those slowing down transitions. So we have the primary electron beam that goes into our sample. It will effectively promote the core electron up to a higher state. This core electron will fall back down, and as it does, it releases the characteristic X-ray. The primary electron can go on and do other stuff afterwards. Of course, it's lost the energy corresponding to that promotion in the process. Now, the characteristic transitions are related to the promotion of an electron from a different orbital upwards, and it's falling back down, and we'll see why that matters in a moment. Specifically, this corresponds later on to the characterization because the X-ray energy is characteristic of each of the different elements that are present, and the energy levels themselves are quantized in practice. If we look at an EDX spectrum, this is a spectrum from some zircaloy that Vivienne Tong collected during her PhD. The x-axis is the electron energy in kiloelectron volts. The y-axis is the number of X-ray counts. So we have a 0th peak, and then we have the characteristic spectrum. The first, we have a background called the Bremsstrahlung, which is located here. And then we have the characteristic peaks. It's a Zirc matrix, so there's a big ZR peak. There are secondary peaks. We'll see where they come from in a minute. And then there are smaller minor elements such as tin, chromium, and iron that are present in this material. How do we generate those characteristic X-rays? Well, effectively, we can get K, L, and M transitions. A K is effectively that we have fallen back down to a K element. So we've promoted up, we've fallen back down. And if we promote up to an L and fall back down, we get a K alpha. If we promote up to an M and fall back down, we get a K beta. An L line is effectively from the promotion and falling down back to the L, and an M line is similarly promotion and falling back down to M. We can see this in practice. Here effectively are K peaks associated with one series of transitions. It's taken from the Australian microanalysis facility. And we can see the characteristic K lines are falling down to the K, and there are a series of different transitions. There are different transitions within the L, alpha 1 and alpha 2. And then there are different transitions from M to K, which is the beta transition. The ratio of alpha to beta is approximately 10 to 1 for most species. And typically we cannot easily resolve the transitions within the alpha because they're relatively small differences, and the resolution of the EDX technique is often relatively small, is relatively bigger than those small transitions. If we look effectively then at the L peaks, we see a much more characteristic fingerprint spectrum, where we see again that there are the alphas that are associated by the M to L transitions. We have the betas in there as well, and we have the gammas that are the high transition drops. So within these, we effectively get the L alpha to L beta to L beta 2, and we get a 1 to 7 to 2 ratio for this set. We see that as a characteristic fingerprint, so they're very useful to spot once you get familiar with your X-ray spectra for your particular samples. M lines, same problem, just effectively falling back down to M and correspond to different transitions here labeled slightly differently. This is typically quite difficult to resolve, but they can be useful for the family identification of different species. Now, one specific incident is that in our materials, we may have elements that have characteristic X-ray energies that strongly overlap. Here is one example, silicon overlapping with tungsten, and I think it's rubidium. In these ones, and that causes problems. Another major one is effectively the overlap of titanium and vanadium peaks that can happen, and that can cause quantification of these species to be very difficult with EDX. I mentioned in the characteristic spectra, so we have the characteristic X-rays within the spectra. We also have the Bremsstrahlung. The electrons, as they go into the material, are gradually decelerated by the matter. As the charged particle decelerates, it interacts with another charged particle to slow down, and that moving particle loses kinetic energy. That kinetic energy is transformed into a photon, and that is what the characteristic breaking radiation is from. This is a continuous generation of X-rays, and that enables us to generate X-rays of many wavelengths through our sample. What we see is that as we change the incoming probe current, we effectively change the number of electrons that will be generated, number of X-rays that will be generated in the Bremsstrahlung over here. The low energy peak is kind of interesting because those are the ones that are generated and escape very easily. Of course, the X-rays have to be generated and get out of the sample. As you change the incoming probe voltage, we see that there is a significant change in that characteristic Bremsstrahlung. The model of this can be useful to understand what is happening in our material. And we can have some very simple relationships. The Dune-Hunt law tells you about the minimum energy of the Bremsstrahlung. The spectral distribution can be written down like this. These are taken from sort of signals that are generated in this description here. Now, the shape of the Bremsstrahlung is particularly indicative and useful to know because that can tell us about the volume of material through which the scattering happens. So in the assumptions that I've shown you before, these assumptions are broadly consistent with having something like an SEM type volume, where you have a large volume of scattering, so the electron beam can scatter from a large volume, and the characteristics X-rays will be generated from those. This volume is, of course, dependent on the energy of the primary voltage, because primary electrons of higher voltage can penetrate further into the sample. Note also that in order to generate those characteristic X-rays, we have to promote the core electron upwards to our high energy state, so we must have the primary electron to be greater than the characteristic X-ray energy. It will also change the interaction volume, not only the scattering to penetration depth, but also the scattering width, and we'll see this is quite important much later. We can reduce this by cutting our sample and effectively removing the scattering around the back to go to a transmission electron foil, where effectively the size of the probe is now the thickness of the foil times the width of the incoming probe. And so that gives us the spatial resolution is strongly determined by how well we can focus the electron beam. Broadly speaking, in an SEM will typically operate between 1 and 30 keV. We'll often look at bulk samples, and we'll typically be able to focus down to something like a 3 nanometer probe with a FEG, which will result in a 1 to 5 micron spatial resolution for quantitative analysis. We'll see with some care we can improve that. We'll see that a bit later in the talk. For STEM, we go to higher voltages, but that higher voltage is useful for lots of things. It can excite higher characteristic X-ray energies. We can also look through a thin sample. And we've got effectively, again, it's the through thickness times the width of the probe will control the interaction volume. So the interaction volume is strongly dependent on the primary kV of the beam, especially for SEM. We can see that the sample preparation of a foil versus a flat sample is quite important. If you have a non-flat sample, that can be very important, and I'll just show sort of an example of where that non-flatness matters. So if you imagine that you've got, in this example with my hand, that you have a sort of slightly tilted, if you scatter the beam into this sort of claw-shaped, that the beam can tunnel through or get through the material, it will go through the material, and the X-ray generation will be from here, and also the scattered volume beneath that could then be perhaps collected at a detector over here. Okay. If the material was bulk, then of course the volume is now much more classical. The nice thing is that the Bremsstrahlung gives a strong indication of the scattering cross-section. So ideally, if you want to do this well, you have a flat sample, life becomes easier. The second point is that if the beam is charging on the sample, then the beam gets deflected, and of course the scattering then goes through material you weren't expecting. And also the other point is it will change the landing energy, so it will change what it can excite inside the material. Our EDX system, the important thing is that we can also characterize the X-rays that are generated. There are two detector types. There's a silly detector, so the detector is located here. The rest is electronics and cooling. This has a liquid nitrogen cooling system. It's relatively large and requires topping up, so it has a whole range of infrastructure challenges. The STD detector is relatively smaller. It's cooled with a Peltier system. It has a much higher efficiency. They cost a lot more, but they're very useful. We tend to use these more often if we can. The STD detector effectively is it's all located. The business is at the tip. The rest is effectively heat sink, to deal with the Peltier system, and electronics to pull the signal off as fast as possible. So this is inserted into the microscope. So this is at vacuum. So the X-rays are generated from your sample. They will go through, and we will collimate to get the X-rays that will go directly through into the sensor. Some electrons may get in, and they could change the signal that we generate. So we effectively have a small positive bias electron trap that hoovers those up, similar to the ETD detector for SE. We then have a window, effectively, so we can have our FET, an STD sensor. We can have those things set up to be near atmosphere. And then we have the window to protect this. In some systems, you may effectively have a windowless detector. That means it's especially important that you do not contaminate the chamber, because effectively you can get contamination building up on the surface of your detector, and it will reduce its quality over time. So the window will maintain the vacuum, and we'll see later it will cut out some X-rays. The sensor, the X-ray ionizes to create charge, and then we use the FET to amplify the signal. We have cooling in the system to reduce noise and improve efficiency of the detector. So inside the detector, we effectively have a semiconductor where the X-rays will generate a number of electron hole pairs corresponding to the energy of the X-ray. Specifically, it's the energy of the X-ray divided by the band gap of the semiconductor. So we ionize atoms in the semiconductor, we create charge, which is converted into a voltage that's measured effectively on our gate on this, on our FET. That voltage is input into a processor, and then we get a discrete energy resolution of the X-rays based upon the band gap of the quality of the band gap of the detector. Now, clearly, the X-rays, to measure them, you've got to see them, and so a larger detector will see more X-rays. We'll see that in a minute. To do the counting, we use something like an old-fashioned FM radio signal. So we have a standing voltage, and each time a hole pair gets generated and gets counted, it increases the voltage of our system, and we see that building up. And then in a fixed time, we chop the signal, we reduce the voltage back to the carrier, and then we let it count up each time. So each of these characteristic this to this is ascribed as one X-ray, and that will go into a count on the y-axis. So the quality of the counting is related to how often you chop this signal. If you chop it really fast, you can get a broadening of the signal. If you count it really slow, you can get two X-rays giving rise to one count. So you get a double peak. So you have to change the processing conditions. The pulse processor settings will change the resolution of the spectra. The important aspect also is how many counts do you get? Well, that's dependent on the solid angle. The solid angle 1 is dependent on the area of the STD that we'll see a bit later. But it's also dependent on the position. So in this example, I've just pulled the detector backwards, and we can see immediately that the solid angle seen by the detector is lower. In this second example, I've moved the sample further away, and again, the solid angle is smaller. So ideally, we'd like this to be, because of the collimator setup, we'd like to be in a sweet spot. Typically, it's around 15 millimeters in an SEM, and we want to have the detector at as close as possible to get the maximum count. And we'll see a bit later, there are specific reasons why you may want to back that off to reduce the total counts. And here are effectively solid angle diagrams to show how that solid angle will vary in the particular examples that I've shown. Now, clearly, you can increase the number of counts by two methods. so we can generate effectively more beam current. So if we can get more beam current, we can get more X-rays generated. The second is if we improve the efficiency of our detector by moving to a better technology, something like an SDD, or increasing the total area of our detector, specifically the solid angle, although within the same generation of detectors. Clearly, effectively, we can increase the area, and so that's effectively what the marketing graphic on the right shows over here. There's of course a balance. This thing costs probably about 10 times less than this thing over here, and so there are a lot of choices to be made. And also, the majority of analysis that people want to do can be done with a few point analysis. You don't often need these very fast, very expensive, and sometimes actually very noisy spectra detectors for the large area systems. The detection limits for EDX, the beam energy must be greater than the characteristic X-ray energy. We've seen that before. And efficient generation of the X-rays, typically we would like the X-ray energy to be greater than a third of the primary beam kV. There are also care, and we'll see this in a minute, related to absorption, subsequent absorption of the X-ray, and other interactions such as the creation of fluorescence or the associated with those X-rays. The minimum energy of the detection depends on the detector window. And of course, the double counting and triple X-ray counting, as well as the resolution of the peaks, can be related to the pulse separation on the pulse processor. To do quantitative EDX, typically you want to use high voltage so you can excite multiple peaks. If that's damaging, you can effectively be careful and use the L or M lines for high Z number materials, or you can reduce the electron dose, and so that can be related to a defocusing of the primary beam. You want to optimize the sample plus detector position to optimize the dead time. So the dead time, very simply, is how long does it take to count and process all of those whole pairs. In most detectors, the dead time should be optimized somewhere between 20 and 50%, so it's doing the maths behind the scenes for 20 to 50% of the time, and that will optimize things. To do that, you can change the probe currents, you can change the position of the detector in the sample to change the solid angle in those systems. In most cases, you'd like a flat sample for quantitative, you'd like it to be well polished, and you want it to be bulk and homogeneous, specifically with regards to subsurface, and you want it to be conductive. Now, the majority of samples we'd really like to look at do not fit those, and so we have to be careful about interpretation. Quantification, it's an art to itself and requires some skill, practice, and experience. Often you'd use something like a ZAF correction to do this. So you have the Z is the atomic number, absorption, and fluorescence. This is as described in a couple of papers. It's created in algorithms, that's in the software. The trick is to look at a standard sample and check that you get a composition that you know before you use this in anger on something that is uncertain. The EDX spatial resolution is typically limited due to the scattering volume, and it's typically around 1 micrometer for SEM. But of course, as we can see, it depends on the kV of the beam, it depends on the Z number and the detection efficiency. Clever analysis can be done if you use something like a simulation, like Monte Carlo, to effectively check and understand the details of when you might worry about these problems. Lower kV can improve the spatial resolution, as we'll see a bit later. But do note that voltage can change the ratio of the peak heights due to a change in the excitation efficiencies, and we have to be careful with the quant. Specifically, we have to tell the software what voltage we're using for the primary beam. Typical EDS energy resolution, chemical composition analysis is around 1 atomic percent. If you want to get this better, you have to be careful and you have to understand what your errors are. Typically, you do standards do this, and you do quant optimization routines related to the detector, the voltage, and the current measurements, and how the microscope was set up. The energy detection limit, the first is can you see the peak above the Bremsstrahlung? That's related to effectively the counts per second, the background count rate, and the time of the background. And you need to use the analytical standard to check this. There are two types of error that will be introduced. So one is statistical fluctuations. Did it, produce an X-ray that went to your detector, for instance? The second is that you don't know what you're doing, or there is something broken in the microscope, and that can be due to the setup and analysis method that's present. They are systematic errors, hence a standard-based method is good to establish your detection limit. In an easier view, so once you have an idea roughly what elements might be present, maybe not the quant quite per se, but you've created some spectra, what you can do is you can move the beam across your sample and map the various chemical composition. A relatively easy method to do this, and we've seen this in the SEM course, is to effectively at each point gate the energy associated with particular excitations, and then we can correlate those with particular speciations. So we can see there's an aluminium-rich region, an iron-rich region, and a copper-rich region. Now, in the combination maps, you have to be very careful. The human perception of color is particularly rubbish, so be very careful about that. So often single element maps may be useful to show the relative intensities of different species. But before we do a map, it's often sensible to look at the backscatter and go, the color variation is broadly Z number dependent. So I suspect that this bright yellow has a different chemical composition to this intensity, to this intensity, to this intensity, to this intensity. And I might also suspect to do a few points per domain just to check the ratio and what the spectra look like before even I bother with quant to see what the chemical variations could be. I can get an idea and improve the spatial resolution if I use something like Casino to do the Monte Carlo simulations. So here I've taken some boron carbide with silicon and looked at the interaction volumes at 5 kV and 20 kV. We'll see the geometry looks the same because it's a Monte Carlo slowing down of matter. We see the same approximations, but we see the scale bar has radically changed. So we see that reducing the voltage by a factor of 4 broadly gives a 10 times improvement in the interaction volume. That can be useful, as we'll see in the next example. Do note that the primary beam should be 3 times the energy of the EDX lines. There's also, for light elements analysis, there's low energy cutoff by the window. This is typically a thin beryllium window for our system, so it's difficult to see the light elements and impossible to see hydrogen and helium. The low kV plus the fine probe can give you a smaller probe volume for light element stuff and improve the spatial resolution. But you've got to be careful about how you set up the pulse processor to improve the energy resolution ultimately. The next is you want to use the best detector. So this is an example that we worked on. So here we can see from one detector system to another for the same material system. We can see there is a better quantification of the different energy levels with this improved detector technology. And specifically, not only does it look prettier, but we see the shoulder of carbon that is well distinct from the Gaussian of the boron. And that enables separation of these two peaks to be done with much greater accuracy. If we get this right, that enables us to look at the ratio of boron, carbon, and silicon in our systems, as well as oxygen, and we'll see this in a minute. This is very useful to determine those peaks and differences. If we look at a boron carbide with some silicon carbide included in it, we now can point the beam at specific locations and extract the spectra, and we can see specifically that this bright domain that has a higher scattering backwards for backscatter gives you the silicon-rich domain. This darker region has a boron-rich domain, so we see the boron peak is much higher. If we do if we check what we're doing very carefully, we can get the stoichiometry to look sensible. Silicon carbide is SiC, so equiatomic. Boron carbide effectively has a 4:1 ratio in this case. When we then line scan, we can see strong variations as we move across the domain. So we've done the spectra, check that it looks sensible. We can then do looking across interfaces and structures with higher spatial resolution. We note that the ratios and stoichiometry vary. This is probably more related to the change in the morphology, which changes the interaction volume. So the ratio of matrix to silicon carbide is varying, as shown by the intensity variation in the backscatter image here. But we can clearly distinguish those two domains very nicely. And we could, for instance, look at the ratio and looking at the errors associated with the stochastic variation from our quant in here. If we then have set this up nicely, played with the pulse processor properly, we can then look in a qualitative sense across this domain. We can map the region. And here we can see effectively that if we map in a qualitative sense, we can see the presence of boron deficient small precipitates, which are silicon carbide rich. We can see in this example, this precipitate is not probably oxygen rich, although it's slightly harder to see because the resolution of the oxygen is not as good. We can see the morphology coming out, that silicon, that edge of morphology is present. We can see that in there. We note, though, that I could not likely give you a quantitative chemical analysis for this particular point because there'll be contributions from the matrix. It's fuzzy compared to some of the more definitive regions inside this large precipitate. So care with that quantitative versus qualitative analysis comparisons. In a different example, Catriona McGilvey, myself, Jun Jiang, Finn Giuliani, we worked with a major oil and gas company. We're looking at the structure and chemistry of a carbonation thin films on iron substrates. What we knew is that there's variable film thickness across the sample surface, so we took multiple maps with different kV. So here are our multiple maps. The presentation has decided to misbehave. One moment. Should look like this. Apparently, it's being stochastic, is what it likes to show. Fantastic news. Okay, we'll look just at this image here. So the image itself. So we got voltage over here, moving down in voltage. We have the elements that's shown here. So for high voltage, the beam goes through the thin carbonaceous region. It excites the matrix, the substrate, which is iron rich, and we see a bright variation in iron composition for that matrix compared to a reduction in the carbon concentration. As you go down in voltage, you become much more surface sensitive, so the carbon ratio seems to go upwards, with the exception of breaking down in the film, where there are effectively holes and we see that iron rich layer. The sweet spot will also change where we see the apparent oxidation of those carbonaceous rich domains, and that's important when we understand the morphology of these carbonaceous films across in our materials. It's now behaving itself in a strangeness. So we can see that by playing with different voltages in our experiments in RSEM, we can understand the structure and variation of these thin films on our substrate and interpret that. We did a range of other bits and pieces with cross sections with focused ion beam and a few other things to understand the structure of these microstructures. So a few tips when doing EDX. First off, be careful about contamination. You will get from sweat, you'll get NaCl being produced, and that will deposit and you'll see those peaks. You'll also get hydrocarbons from oils on your fingers. They'll crack and change the carbon chemistry, as well as other mess and things. So clean samples, wear gloves, etc. All very important. Specifically, having a thin film on the surface will increase the interaction volume and therefore decrease the spatial resolution as well. For charging samples, you may wish to coat your samples, suggesting that you use carbon where you can, because you have to be careful about overlapping peaks with your material, and of course the thickness, and worry about that. So you want a nice thin layer that's enough to dissipate charge, but not enough to reduce the EDX analysis. It's important to bear this in mind when you do quant analysis and thinking about the chemistry and variations. Often in analysis, actually, what I'll do is I'll say there'll be carbon present, but I will remove that from the atomic percent calculations. One thing is also the software is very good at just giving numbers. You can very quickly get some numbers. The question always is, do they mean something? So this is where showing the process where you have a spectra, you trust the spectra, you look at the chemical analysis, you look at the errors associated with it, you check that it's behaving itself on a standard, and then you step through and then you say, okay, so now I want to run a map, so I will compromise on the quality of the data to look at the 2D distributions. I won't start the problem to look at the qualitative map because I won't know how to set it up very well. So all of this automation is very nice, but you want to be an intelligent user where you're using stuff sensibly in your process. The other aspect is light elements can be tricky to analyze. We noticed that the hydrogen and helium do not generate the characteristic X-rays. Beryllium to neon can be tricky due to absorption, chemical bonding, and detector window effects. Carbon is always present, often also introduced due to coating and the hydrocarbon contamination. And oxygen can often be better analyzed by looking at the cations of what it's bonded to. One specific thing to worry about is if you have low Z number precipitate in a high Z number matrix, effectively the electrons will strongly scatter from the matrix because they'll escape the low Z number precipitate. And this is also important when you have roughening due to, say, different polishing rates. And so you get variable interaction volume sizes, and that's important. You can detect the signature by looking at the background radiation profile. If the Bremsstrahlung looks weird, be nervous about the quant analysis. Importantly, we've seen you need to choose an appropriate voltage and sample preparation route to show the data that you want to know. In order for you to get the most of this, you can use correlative approaches to effectively down select what you want to analyze, so choose different regions that have different backscatter colors before going to EDX. You want to do an experiment to optimize the pulse processor to get the data as quickly as possible, but with the precision that you need. If you have tricky problems, do simulations. So one example is using the casino algorithm and software. Relatively easy to use. I can run it myself very quickly. This is important for things like interfaces or small precipitates in materials. To summarize, X-rays are generated from the electrons interacting with matter. It's a relatively simple technique to generate the signal. It's relatively easy to qualitatively understand the spectra, but significantly more difficult for quantitative analysis. There's a number of references. I've given a couple throughout the talks, but also have a look at the fantastic resources from the Australian Microanalysis Facility. With that, thank you very much for your attention, and I welcome questions. You can drop me email or you're in the Q&A session after this.